Hi there, my name is Ryan Villarino, and today we're going to be going over the final project for FSE355, in which we were assigned to make a group project doing some analysis on a live fire burn that took place previously, and we're going to try and make some predictions as to what that was going to do before the fire even happened. So to start off, this was supposed to be a group project. We named our group the Panda Group, called ourselves Panda Testing. Group members were myself, Ryan Villarino, Amanda Cherry, and Scott Railing. As of today is Friday, May 10th. I did not receive any information from my other two group mates, so my project was done solely by myself and is probably missing some information necessary to make good conclusions on the project. But that being said, we'll get on with the things that I did, and then we'll get back to the analysis and some conclusions I made from my analysis. So starting off, the tasks assigned to me were A3, B1, and C2. So starting off with A3, I'm going to try and use the iPad to give some visuals with this presentation. Whether or not that'll work, I guess we'll see. So section A3. This portion of the project, I was to create a graph of ventilation opening size versus fire size required for flashover for the given test compartment. A compartment twice as big and a compartment 3 times as big. So, let me get the iPad here. What I did for this project that may be a little different from what some other people did is I took the actual size of the compartment, which you can see here, maybe. Let me adjust my camera. Here's the actual size of the compartment. It basically broke down to 4.27 meter width by 4.87 meter depth and a 2.44 meter height, which is a standard 8-foot height for any room. And then you had one opening that was 2.21 meters and 0.99 meters wide. So what I did that was a little different, as you'll see on the iPad here, is instead of just doubling the total area of the compartment, what I chose to do was double the actual size of the compartment, which gave us double the height, double the width, and double the depth, and double the ventilation opening there. I also did the same with triple, as you can see here. Same difference, just again tripling each individual dimension as opposed to just tripling the total area of the compartment. So in order to calculate the heat release rates that were necessary to achieve flashover, I used the equation Q dot flashover equals 610 times HK, which would be the effective heat transfer coefficient in kilowatts per meter squared Kelvin, and that's multiplied by AT, which is the total internal surface area of the room in meters squared, which is what's affected by doubling and tripling the size of the opening, and also the area of the ventilation opening and the height of the ventilation. So this whole equation reads Q dot flashover equals 610 times the square root of HK times AT times AV times the square root of HV. That was the equation used. Let me just go ahead and give you a quick visual demonstration of the outcome of that in the form of a graph that I created for the 3 different compartments. So here's our graph, ventilation opening versus fire size. And it's kind of hard to make out here with the iPad, but as you can see, you have a top, middle, and a bottom line there, all running pretty congruent to each other. And as far as the analysis went, the 3 lines there compared to the 3 different sized rooms, the bottom line ended up being the actual compartment, the middle line double the size, and the top line being triple the compartment. Each line kind of just interesting point. They all fit an R squared value of 1 to a power equation. and each power equation for the actual size of the room was y equals 1069.2 times x to the 0.5. The double the compartment size was y equals 2152.2 x to the 1/2 power, and the triple the size compartment ended up with 3207.6 times x to the 0.5 power. So, and again, those curves fit the data exactly. So, like I said, I plugged in all the values as you saw before into that equation that I gave before, which ended up giving me those graphs. And I also, in this section, did a quick table. Pull it up on the iPad here, see if it'll demonstrate a little bit of the math that was involved. So it's going to be a little bit hard to see just because of the size. Let's see if I can actually get a good picture on it or not. Well, at any rate, that's the table. What I did was I took the ventilation opening and I just started with a standard height of 1 foot and increased it by 1/2 foot all the way up to 10 feet, and did the same with the width. Multiplied those together to get the feet squared, and then I converted each of those, the height and the width, into meters, and then got a ventilation opening size in meters squared as well, which is what I ended up using. The estimate height of the opening stayed constant at 2.2. It should be 2.44 meters. Let me zoom in, double check here. Give me 1 second. There we go. Get down to my table here, which of course is lost. Give me 1 sec. There we have it. So the estimated height of the opening was 2.14 meters. Standard height of a door, that's how I determined that. I looked up the standard height of a doorway, and that's what I used. The total compartment area for the actual size of the room ended up being 84.01 meters squared. Total compartment area for the double, 340.39 meters squared, and total compartment area for the triple gave us 756.05 meters squared. And with that, you got the associated heat release required for flashovers, which was done by the equation and shown graphically in that graph. Various numbers, each one had a different maximum, of course. For the bigger the ventilation size there was, the higher heat release rate was required for that room to enter flashover, which is kind of what we would expect. Being in the fire service, we know that ventilation reduces heat, and that's why we perform that function. So when we see a bigger ventilation size, we expect for the heat release rate to produce flashover must increase, and that's what the data actually showed. So I think that's about it for A3. If you guys are interested in the data that I got, shoot me an email. My email is tacticalff09@gmail.com. I'd be happy to share the information that I got. Moving on to, let's get my my setup here back the way it's supposed to be. There we go. I don't think there was really anything else interesting about that. I did some hand equations just to verify my Excel math was correct, and everything was. That's shown in my report. Again, the results of this in relation to what firefighters need to know is just basically that ventilation size, when you look at a compartment and realize that windows are open or doors are open, that if a fire is reaching a flashover stage, it has reached a temperature that is probably inhabitable. by any persons and might not be a good idea to make an interior attack on. So it's just something to consider, that if a room's getting that hot and it has ventilation, then you probably have bigger issues. It might be more of a surrounded operation. So moving on, next task I performed was subpart B number 1, and this portion I calculated the approximate temperature a detector would be exposed to if the detector were located where the thermocouple tree is located in the live burn experiment. So I used Alpert's correlations to calculate the temperatures given off by 5 differing steady state fires, and the results were plotted on a graph to visualize and compare the results. For this equation, we had a choice of 2 different equations, which would be the temperature at the detector equals the ambient air temperature plus 5.38 times the heat release rate divided by the radius to the 2/3 power, and that's divided by h. Again, the ambient air temperature is added to that whole second part. So when the radius over the height is greater than 0.18, we use this. When the radius divided by the height is less than or equal to 0.18, we would use a different equation, but this wasn't the case in either or in any of calculations that I use. So we'll just use that first equation for this. To obtain the different steady state fires, I simply just looked in the book at the different items and different heat release rates that they produced. So I used a polyurethane sofa, which gave us a heat release rate of 3,000 kilowatts, an upholstered chair with polyurethane foam padding, which gave us 950 kilowatts, a polyurethane chair, which gave us 2,000 kilowatts, wooden dresser, which I compared to that end table you can see pictured in the experimental data, and that gave us 1,700 kilowatts, and a television, which would be common in that room as well, 570 kilowatts. All the pieces of information that I gathered were used with the intent of something that would actually be in the burn room. So let me show you my results here, again as best possible. So this is the graph that was produced, scatter plot anyways, which basically you can see the temperature is on the left hand side there with the corresponding heat release rates at the bottom. You see 5 different numbers there, and those all increase proportionately to the size of the heat release rate of the fire, which again is to be expected. The bigger the fire, the higher the temperature in the room is going to be. Additionally, this also produced temperatures in Kelvin, which had to be converted to Celsius, which I used an Excel spreadsheet to do. Let's see if there's anything else interesting on this. Checking. I also created a table, which basically says the same thing. It basically gives us the inputs that were used and the corresponding temperatures that were given off here. You can read that, pause on that if you need to. Ambient air temperature was assumed at 298 Kelvin, as has been for the entire course, so that's what I used for that. The detector location was assumed to be where the thermocouple tree was, and I'll show you how I did that analysis as well. So basically I used one of the photos from the burn. Let's see if I can get this oriented the right way. There we go. Let's see what we can get here. That's pretty good. So you can see the height there that I estimated. That was the measurement I actually took and compared to an 8-foot height that we knew that the room was from our problem that we did in section A. And then I used the radius to the couch there, where you can see the firefighter actually ignite the couch. That was the spot I used for that. And just to kind of go back to A, this picture right here is what I utilized to get the height of the room, which turned out to be just a standard 8-foot height. I took the height of the man, assumed him to be 6 feet high, and then took a measurement from the floor to the ceiling, compared the two, and generated a height of 8 feet. So that is that for section B number 1. and moving on my task into C2, where I actually use CFast to create a zone model, and I was to create 3 different zone models utilizing CFast and a few different ventilation configurations to do so. So instead of going through everything and telling you exactly what the heights and widths and stuff, since we've already gone through all of that, I'll just tell you the particulars of each model that kind of changed. We used the burn room, the exact dimensions that were shown in the A portion. The hallway that I added, as asked in section A and B, the hallway that I used, I made a width of 1.25 meters, depth of 4.87 meters, which was the depth of the room in general, and gave it a height of 2.44 meters, which would be the same as the room. The first assignment, section A, what I titled it, was with horizontal flow vents from the burn room to the hallway. To do that, I gave the hallway, and the burn room was offset. I'm sorry, this vent was offset in the burn room by 0.2 meters, and it faced to the right. So this would be from the burn room to the hallway, a doorway going into that room. Gave it a sill of 0 meters, soffit 2.21 meters, and a width of 0.99 meters, and again was facing to the right. And we had one more vent in this scenario, which was the hallway to the outside, with the offset of 0.1 meters, sill 0 meters, soffit 2.21 meters, width of 0.99 meters, and this vent faced to the front, so it would simulate like a front door. Let me show you what the CFast model actually produced for this and how my model actually ended up looking. So as we look at this model here, you can see the fire, which would be in the back left-hand corner of the room. I tried to make this as close to the actual burn as possible to simulate. So you can see the vents in the front there. You can see the hallway, which would be off to the left, and the doorway leading into the hallway, both venting there. So this was done at some point during the CFast. The main reason for the images was to show the geometry, and that the actual smoke view did run and produce results in this. So what we got using that model, we'll just go through all the models first, and then we'll go to the actual determinations made by the models. So next was, I called this C3B, which was the zone model 2 assigned. And again, we had a burn room, and we had a hallway, and we had vents, the same vents utilized before, with the addition of one window, which went from the burn room to the outside. So I offset that in the burn room about 1.2 meters, which would basically center the window in the room, and I made the window a height. I used a 4 foot by 4 foot window, which I think is average for a home like this. So I assumed a 4 foot by 4 foot window. In order to accomplish this in CFast, I made a sill of 0.76 meters, soffit 1.68 meters, and a width of 1.22 meters. I'm sure you can hear kind of the differences there. It doesn't actually add up to a 4 by 4, but when doing this in CFast, it's more concerned with the height compared to the wall, as opposed to the actual size of the window, so that's why that is that way. For the fire, again, in all 3 of these, I'm going to use a sofa fire in the burn room, just as was seen in the actual burn. And then model 3, what you had, instead of the actual hallway, the hallway is eliminated, and I called this C3C. Eliminate the hallway, sofa burns in the same position, that room remains the same, and the only thing that really changes in this model is the fact that the hallway is eliminated. Here's a demonstration of the second model. Go back to that real quick. You can see hallway with a vent, burn room with a vent into the hallway, and then the window leading out exactly to the outside. So back to model 3. Again, in this model, you just lose the hallway. You get a vent, 2 vents that actually exit straight out into the open. So those were the 3 burn room scenarios used. For that, first thing we'll show you is the upper layer temperature given off by these 3 rooms. Now, what was a little interesting to note here is that last model, C3C, is the one that actually produced the lowest temperatures. So we had two vents venting to the outside, and that was able to produce lower temperatures than anything venting into a hallway and then venting outside. So any sort of obstruction led to a higher temperature in there. And it also, as you can see on this graph, without the obstructions, that top line that you see there is C3C. So C3C with no obstructions gave a, how do you put this, lower, a higher height, I guess you could put it. So the actual temperature, or the smoke layer would drop down less than it would in the other ventilation scenarios where there was a hallway. So either way you put it, there would be a more tenable situation if you had 2 vents venting to the outside than with an obstruction as the hallway, no matter if there's a window in the front or not. Again, that window in C3B did make it more tenable than C3A, which went straight to the hallway and didn't have a window out to the outside. So the conclusions reached from this, let me show you one more quick table here that I did with this data. And I'll let you pause it and take a look at this if you'd like. Here are basically C3A, C3B, and C3C. And you have a comparison of the time, the upper layer temperatures, and the heights of each, which will demonstrate exactly what I just told you, that basically the less obstructions and the more open to the outside world, the more tenable the structure is going to be for anybody inside trying to make an escape, or it's going to make it easier for firefighters to effectively put out the fire, because they're going to be able to make a better assault on the fire with that ventilation. So a couple good things to note out of that is ventilation's key. I think we all know that, being firefighters, that the quicker we can get on fire and ventilate, the better it's going to be in most scenarios. Obviously there's a few scenarios, and we all know those, where that's not the greatest idea, such as backdraft conditions, that sort of thing. But that being said, the models show that if you can get ventilation on a fire, you'll be able to cool the room more effectively than if the room is more obstructed or closed to that ventilation. So now moving on to subpart D of my project, which we were just asked a few questions. I'll just go ahead and read my answers for you. For subpart D, part 1, I have the modeling efforts were unfortunately limited in this group project. Of the 9 subsections that were contracted to be completed by 3 persons, only 1 person partook in the efforts, myself, and as such, only 3 subsections were completed. The subsections completed were the ones I just talked about, section A3, B1, and C2. And these subsections models were used in order to project results from an actual fire. So we used hand calculations. I used Excel spreadsheet calculations, and I also used the fire modeling program CFAST in order to make these determinations. So section A3 utilized hand calculations in cooperation with the use of Excel spreadsheet in order to predict heat release rates based on given compartments and ventilation within them. While the results are interesting in this section, there's no applicable value to the actual data gained due to the fact that other sections of the project were not completed. So if I would have had more information from the A sections, I think it would have been more applicable. If I would have had my partners' portions of the project, I could have compared and contrasted a lot more than what I was able to do with just the one section by myself. So that being said, we did get some good numbers and some good applicable data from that. Section B1, I used hand calculations in a spreadsheet model In order to calculate the temperature a detector was exposed to at a location of the thermocouple tree in the actual burn, as we talked about. This detector ended up being at a location 8 feet high and a little over 3.5 feet from the fire. 5 differing steady-state fires were utilized to calculate the temperature the detector would be exposed to. The steady state is assumed as the point in the fire is no longer growing and has not begun to decay. As such, the highest temperature measured by the thermocouple tree was utilized at the 8-foot height. And when compared even with the highest release rate utilized in steady-state fire models, the temperature to the detector basically grossly underpredicted what the actual fire produced. So the max temperature at the 8-foot height on the thermocouple tree measured to be 993 degrees Celsius, while the model only predicted a maximum temperature of 455 degrees at that detector in that time frame. And in C2, CFAS was utilized with different ventilation configurations in order to analyze many aspects of the fire behavior. And then compared to the thermocouple tree, CFAS did an okay job predicting the conditions present in the fire. So CFAS predicted a maximum temperature around 840 degrees Celsius, while the actual measured temperature by the thermocouple tree reached about 995 degrees. So the major difference between the two was the time it took to reach those temperatures. And the actual data is a much faster curve, while the CFAS model produces a smooth curve. So what you see when you look at the actual data, making it in graphical form, is kind of a quick spike with a quick fall. What I attributed that to was the fire suppression effort to have that quick rise, and then you have suppression, which makes basically the graph fall off. Well, CFAS produces a nice smooth model which goes up, comes down, plateaus, comes down, and reaches its steady state of decay. So again, I attributed that to fire suppression efforts, and then also the fact that CFAS only predicts a fire on the sofa, and it does not actually use the surrounding area, the surrounding contents to create that fire. Whether or not that can be done, I don't know. I think that would be beyond the scope of this course. So I think it did a decent job predicting what a couch fire could do in the given compartment. That being said, I would use it more as a guide to start before you have a fire like that. If you're going to use it to compare, like in a court of law or something like that, there are so many limitations that need to be expressed and make it understood that it's a limited program and it's just a general idea of what could have happened, not what actually did happen. So with that being said, I thought the CFAS model did an okay job and probably did the best out of any of the calculations that I was able to do. Like I said, I didn't get to see all the sections that were to be done, so I think the CFAS model was probably the easiest to use because it was there was less things to mess up. Everything was pretty lined out as to what goes where, what was what, and just easier to input for me, having a computer-based background. So when the zone models were changed, as you can see, ventilation outputs were changed, made higher ventilation area, and then lower temperatures were produced. Let's see. I also thought that CFAS produced the most aesthetically pleasing of all the programs. While with the Excel, it's pretty easy to make graphs and stuff like that you saw in my data. It does a decent job displaying it, but when you can put that fire in a room and show somebody this is what could have happened, I think that does a better job displaying the power of the fire than what just a curve could do. So I like CFAS for that reason. So if I were actually the consultant used on this fire using that data, I would most likely run most of the calculations that we did here in the same manner. However, I would definitely make it known that this is not actual factual data, that there are many limitations to each of these calculations, that there are many assumptions made in each of these calculations, and as such, you kind of have to take it for what it is for that. So that was my group project, or individual project, I guess you could call it. I thank you for your time. I thank you for watching, and I hope that you gained some information from this. and have a good day.